Hi, this is Mr. Warden. Here's a key for exit ticket 14.1. So in this first case, you've got four cards on a table. There's a 5, there's a 5, there's a 4, and a 7, and you're not able to look at them, and you're not psychic, apparently. So what's the probability you will pick a 5 and then a 4 at random if you put the card back on the table and had someone mix it up? So that is going to be this. So there's a probability of 5 and then a 4. So these are compound independent events. It's compound because there's more than one thing that has to happen. And it's independent because the second event does not depend on the first event because we put the card back in. So its probability of a 5, then a 4 is going to be 2/4 times those 2 out of 4 chances for the 5. And then there will be 1 out of, now still 4 cards because you put the card back in, 1 out of 4 chance for getting the 4. So it's 2/16. This 2/4 times 1/4 is 2/16, which simplifies to or reduces to 1/8. Now here we've got, let me just copy what I've just done in here because the second scenario is a little different. We did not replace the card we got. So that makes it compound dependent events. And so our probability is going to change. Okay. So it's still, I'm going to write it down here. So it's 5, then 4, no replacement. So the probability still of getting a 5 is 2 out of 4. However, once you have gotten that 5, now there's only 3 cards, and only one of them is a 4. So it's 1 out of 3 cards now. So in this case, the probability has now increased slightly. So it's going to be 2 times 1 on the numerator and 4 times 3 on the denominator, 2/12, which is 1 out of 6. The probability increased slightly because there was a smaller pool, a smaller, what we call a sample space for the second pick. So there was a 1 out of 3 chance, a much higher probability than a 1 out of 4 chance. And so we get a 1/6 probability for the overall compound dependent events for that. Now, in the third one, we're going to take a look the order. So we're going to get a 5 and then a 4. And the order doesn't really matter. You just need to end up with a 5 in your hand and a 4 in your hand. So would the probability change from 2b? Well, in fact, it would. It would double. So we have the probability. So we have a probability of I'm just going to copy something from the previous one. So we have that, or this. So when we have that situation, we actually are going to add our two probabilities. So when I say or, instead of multiplying, I'm going to add those probabilities. There are some cases where it gets more complex, and this can produce bad results. But if it's this situation, we're not going to end up with some probability greater than 1 by adding the probabilities. We can do this. If we end up with a probability greater than 1, then we might have to first figure out the probability of not getting this sort of thing and then subtract that from 1. So the probability of getting a 5 and then a 4, no replacement, we just worked out. It's 2/4 times 1/3. So there's 2 5s to pull from out of 4, and then there's 1 4 out of 3. So it's, that one is 2/4 times 1/3, which equals 1/6. We already worked that out. But over here, we've got this probability of a 4 and then a 5, no replacement. So that's 1 out of 4 times, well, there's still 2 5s out of 3 cards now. And 1/4 times 2/3 is 2 out of 12, which equals 1 out of 6. So it turns out there's 1/6 plus 1/6 probability. Okay, and that's going to be 1/3. 2/6 equals 1/3. Okay, so that is going to be the possibility. So another way of thinking about this is we take this probability of 1/6 and we'll end up dividing it by 2 factorial because there are 2 different ways to arrange our results. So 1/6, so we'll multiply it by 2 is what I mean to say. So we're going to double the probability because there are 2 different ways that our results could happen. We could win 2 different ways. So we double our chances to 1/3. All right, I hope that helped.